Hi everyone, you're in the session for ingesting GIS data for your XR experience. My name's Steve Lee and I'm the cross reality or extended reality lead at Telstra Purple in Australia. And this talk will basically give you a foundational understanding of what GIS data is and how you can use it to enhance your VR or AR experiences. So what is GIS? Well, GIS is shorthand for Geographic Information System, and it's basically the way that we talk about the real world, whether we're describing roads or buildings or landscapes or whatever. GIS systems hold that information for you. And increasingly, we're seeing a desire to bring in more and more of the real world into our VR experiences, whether it be for things like enterprise training or whether it's for AR experiences that exist within the world. And all these can come to light if you can find the right data and you know how to use it properly within your application. So my first piece of advice, which I'll get out of the way before I even start this talk and get into the meaty content, is to not roll this stuff yourself. Uh, most of the big providers of GIS data that you see at the consumer level, that is Google Maps, Bing Maps, or Mapbox, they all have controls to do this sort of thing in Unity and in other platforms as well. And generally, reach for those controls to do anything that you want before you start trying to roll this stuff yourself. It may seem simple to begin with. You know, we're all 3D programmers or designers or whatever. We know how to do this right, but GIS is much, much more complicated than it seems to begin with. So first piece of advice, don't roll it yourself. But let's move into it. And the first bit about GIS is that it describes the world. And the question is like, how does it describe the world? It's just GPS coordinates, right? And that's true to a degree. If we look at our Earth, it's a sphere, pretty much a sphere, pretty close to a sphere. And any point on a sphere can be represented in two angles. When it comes to Earth or planets, we use latitude and longitude to refer to those positions, those angles in the sphere. So if we look at latitude here, it is the angle that is up or down from the equator, the center point that runs through Earth. So going north, we have positive latitude, and going south, we have negative latitudes. Longitude is the angle around the Earth, running to the east. And 0 degrees there is called the prime meridian, and that just runs through Greenwich in the UK. So I don't know why Greenwich, it just is Greenwich. Now we have to deal with that. So even that sort of simple explanation, it's easy enough to understand, but there are a few gotchas that I can almost guarantee will get you when you're trying to implement some of this stuff. So the first part is just remembering which way around latitude and longitude are. So latitude is the way up from the equator, as I said before. I remember this one because latitude sounds a little bit like altitude, and altitude is up and down. So there you go. Latitude is the angle up or the angle down. Um, Other people say, well, longitude's easy to remember because it's the longest line that goes around the world instead of just halfway up. Whatever helps you remember will be useful. But the other gotcha here is that if we look at the coordinates for Brisbane, the Earth is actually 22 kilometers fatter around the equator than it is around the poles. And so we represent this as an ellipsoid. And it is the most sort of geometrically simple way of referring to altitude is distance from that Earth ellipsoid, which is a well-defined figure. That said, most countries use their own version of altitude as a reference point. So, for example, Australia has the Australian height datum, which is basically a data set that says these points are at these heights and smoothly interpolates between them to account better for changes in density at the surface and hills and things like that, which just gets a bit of accuracy when measuring with devices. So you sort of have to know what reference system you're in for altitude, but the simplest explanation is just using the ellipsoid version and then converting to that will make it well supported across all platforms. So we sort of described how to say here is a point on the Earth or above the Earth, but that's not actually very useful in practice because that's talking about an ellipsoid, and most data sources that we want to deal with are about flat things. We've been flattening the globe since forever, and there's a new resurgence to flatten the globe. But the way that we actually represent the globe in a flat way is by using what's called a projection. This is roughly similar to a UV map. So if you see a UV map of a face, you see it's all stretched out. And we do a similar thing with the Earth as well. We stretch it out as we need to do. There are a whole bunch of different projections. Even Flat Earth Society's logo there has its own projection, which it believes in, which flattens it out around the North Pole and puts the South Pole around the outside. And that is actually a valid map projection that you can use, and it has its own benefits. But for the most part, we use this projection here, which is called the Mercator projection. It's an extremely useful projection for cartography and navigation, especially because north and south, east and west on these maps represent, the lines on these maps represent the compass points, north, south, east, and west. So it's a good way to flatten that sort of stuff out. At any local point, those north, south, and east and west are perpendicular, which is handy. It's actually extremely handy. On the downside, though, it really, really, really distorts things around the poles. So the way it works is essentially cutting a line around the Earth opposite Greenwich, so opposite the prime meridian, and then stretching the whole globe out beyond that. And as a result, the things that are closer to the poles get more and more and more stretched out. So here's a bit of an animation which you may have seen before of the real sizes of the countries or the continents, actually the countries, versus the projected size of it. And you can see, especially with Antarctica and Greenland, they are severely, severely distorted. Greenland looks 3 times the size of Australia, when actually it's about 1/3 of the size of Australia. So keep that in mind when we're dealing with the Mercator projection, that there may be some distortions in the sizes of things, but the way we consume it in tiles means that there's no skewing. Things are still the same amount of stretch on the X and the Y axis for the most part, which I'll cover in a moment. So the way that we consume or that we read data from one of these projections is by the use of tiles. You can think of tiles as roughly a level of detail texture map for the globe. And the standards basically dictate that a tile has a zoom level, an X, and a Y. And at zoom level 0, the map resolution is 256 by 256 as per the standard, and there's just 0, 0 is the map coordinate for this one tile. We can go down to zoom level 1, which subdivides that, and you see the map resolution goes up to 512 by 512, and there are different coordinates that you can use to get those tiles to render. As we move down to zoom level 2, once again, we split each one into 4 again, we get even more detail, and now our map resolution is 1024 by 1024. If we go crazy and we go to zoom level 19, which is the highest level that OpenStreetMap supports, we see that our map resolution is 134 million each direction, and that our tile numbers are in the 500,000 range here. So we're at sort of block level accuracy at this point. The highest zoom level I've seen in practice is 21, I believe, which was a high detailed photogrammetry capture of Brisbane CBD, which had 2 centimeter accuracy on each of its points in the point cloud, which was really, really impressive in my opinion. So these are tiles that you can use to sort of paint the base layer of your map. And in order to get these things, often you want to base your origin around a latitude and longitude of interest. So you might want to be in the middle of your city. in which case you'll need the latitude and longitude of the middle of your city, and you need to sort of ask yourself, what's the tile coordinates for this, and what's the zoom level that I want? I've got a link here for an OpenStreetMap wiki with a page called Slippy Map Tile Names, and that actually has a whole bunch of implementations for converting to and from these tile coordinates. And these tile coordinates are supported in all major platforms. You've got Google, Mapbox, and Bing. Again, you can pull down these tiles. You can use the formulas in the Slippy map here and pull down your tiles. But once again, don't roll this stuff yourself. Your map vendor almost certainly already has tools for this. So get me the tile at this location without you having to worry about the map behind those tiles. So I want to move into a demo of how I've used these tiles to form a base layer for an application, which was for a company that sold farmyard products. So think cattle yards and things like that. And they wanted a farmer to be able to see these products in place on their farm in virtual reality before they sold them, just so they could get an idea of space concerns, how close it will be to the road, and essentially try and give them that warm, fuzzy feeling of here's some shiny products on my yard. Please buy our stuff. So the first tile that we go to retrieve is a road map. So a symbolic map tiles, which through the Google APIs, you can actually style individual tile layers as you want. So in this case, I've styled it so that the ground is red, that the water is blue, and that the road is green, because I want to map those to textures when I'm rendering this stuff. And so you have a look at the request there. It's not small. The bottom 2/3 of it is all about style. So I'm turning off labels and turning off administrative boundaries and things like that. I just want to keep the ground, the water, and the road. At this point, for this particular API, it doesn't support tile referencing in the format that I described earlier. And so in this case, I'm just passing it the center point. But the points about the zoom level and the resolution is still valid. So once we've pulled down that map tile, I also want elevation tiles. And this one here, the best source I found for elevation tiles is Mapbox in terms of simplicity and price. So I'm using Mapbox here, and you can see this does support actual tile formats. And so there's sort of 4 parameters to this particular API, one being the style. So I want Mapbox's terrain RGB, which encodes height into red, green, and blue, down to about 10 centimeter accuracy. The zoom level, the X and the Y of the tile. And I can apply that formula that you can see at the bottom there, which will give us the altitude of that particular point in reference to the ellipsoid that I mentioned earlier. So just with those 2 tiles and a nice, happy, fun shader later, 5 points, you can guess what 3D engine I'm using here, we have a rendered landscape just by doing those, applying the height map, painting it with this shader, and there we go. We can see we've got a dam there, some roads, and the base terrain, just the dirt, or dead grass as it turned out. So this is great. You put this on a farmer's head and they say, I don't recognize this place at all. And the reason for that is that we're missing more detail. All we have here is roads, the ground, and the dam. We found that trees were a big change here. Like adding the trees made a big difference. And so how can we add trees? Well, let's go and get the satellite image from Google as well. So here I am making another request to the static map API. This time I'm using the map type of satellite. And you look at this, this view and you can see that trees are dark green and there's really nothing else that's dark green. So what I do is I pick up 300 trees and I throw them at the tile. And I keep the ones that land on a dark green spot, and I throw away ones that land in other places, and I also throw away ones that land on the road or land on the dam as well. And when I just do that, you can see we've got a pretty good indication of this area. And it was actually at this point that the farmer could say, oh, I understand where I am now. That's that dam. Even just adding the trees and then being able to look left and look right and say, oh, there's not many trees this way. I can see the trees on the hill up there. It made a really, really big difference to them being able to recognize it, which was fantastic. So we didn't have to go into further detail about trying to map out buildings and things in this particular project, but I'll cover how we would do that in the next part of this talk. One thing that's fairly important is thinking about the scale of this tile or this 3D experience. So when we put a product on it, it is actually scaled to the correct size for someone to walk through, and it's not misrepresenting things. The reason I bring this up is because tiles can be a little bit skewed, let's say. So this is a tile that contains the satellite imagery for two stadiums. The one on the left there is in Los Angeles, and the one on the right there is in Sweden. And each of these stadiums have a running track around them, and a running track has a 100-meter sprint section. And we can see I've colored in, I put an arrow on the 100-meter sprint section uh, of each of those, and I've pulled those arrows out and put them next to each other. And you can see that the one in Los Angeles is a lot shorter than the one in Sweden, even though the tile size is the same. This is a thing that you'll come across, and essentially it comes back to our good old friendly Mercator projection that I mentioned earlier. So even though when you think of us doing a sphere normally, you sort of stretch it out a bit around, like to flatten out around the prime meridian, and then you just stretch out the rest, and that gets you your map. Well, they knew that this would skew things. It would mean that things close to the equator were the right aspect ratio, but things close to the poles would be stretched in one direction, would be stretched horizontally, but not necessarily vertically. And so when they cut up the tiles for these sorts of things, when they did this projection, they actually used a pretty complex function to simulate the curve to maintain aspect ratio across it. Even on the left here, when you see those countries shrink in size, you can see that the countries don't actually morph in size, and that's morph in their appearance. So yeah, this projection is quite clever at maintaining local aspect ratio while while allowing flattening and despite the skew. In practice, what this means is when you're rendering a tile, you need to go to that Slippy map webpage I told you earlier and make sure that you're getting the right real world tile size for your zoom level at your latitude. So tiles close to the equator are actually smaller than tiles that are closer to the poles. Again, use a mapping library, it'll do it for you. You won't have to think about it too much. So that leads us to the end of the tile part of this, which is a good foundation to use for any GIS experience. You can pull down the tile data that you need and do whatever visuals your artists want you to do or your designers think that'll be good for our users, and use that as the base foundation layer for your map experience. Whether that be a small map that you're sort of just exploring on the table as like a top-down view, or whether it's an immersive scale thing, those tiles make up the foundation base layer. But as you saw with that one, we only had roads, trees, water, things like that. And even the trees were a bit of a hack. Um, Often for these things, you want more detail, more detail. So we're thinking things like buildings, things like pipes that are running underground if it's for engineering purposes. You might want things like power poles and traffic signals that might be useful for your game that you're dealing with. If you're making a racing game, you might want to have realistic traffic lights and things like that. And all these are encoded are called what's called features. They roughly translate to meshes in a normal 3D kind of space, but it's pretty loose because there's a whole bunch of different types of features that don't really translate to meshes one-on-one. Now, the great thing about standards is there are so many to choose from, and that is certainly true in when it comes to GIS storage formats. And so here are the four that I've seen as the most popular. So we have GeoDatabase, which is basically a SQLite database that holds all of your geographic data, including tiles, but also features. You've got GeoJSON, shapefiles, and KML. So GeoJSON is a bit of an open format loved by the JavaScript community more than others. KML is the main language that things like Google Earth and Google Maps speak when they talk about their features. And shapefile is Esri's format. So you'll see that coming a lot out of products like ArcGIS, things like that. But at the end of the day, that'll be a feature, and no matter what storage it uses, a feature will contain a whole bunch of things. One of those things is an identifier, just a unique identifier for the feature. There'll be a whole bunch of custom properties, and this will really depend on what you're doing. If you're modeling a bunch of pipes coming out of a gas refinery or something like that, then your features will have flow rates, and your properties will have flow rates and things like that. If you're doing lot boundaries around houses, they'll have things like the price. If you're doing buildings, it'll have stuff like the roof height and the number of floors. That just depends on your provider, and so you've got to think about what you want to expose to your users for those. A feature will be defined in a particular coordinate system. So we've been talking about the Web Mercator coordinate system, which is there as WGS AE4. But a lot of the times features will be in a different coordinate system entirely. So Australia often uses the GDA 94 format, which just reduces the amount of skew around Australia since it's 35 degrees down for the most part. And the other thing that's in a feature is probably most interesting to us as 3D devs is geometry. So you'll have points, you'll have lines, you'll have polygons and things like that defined in the feature. But no matter where they come from, no matter how they're defined, you've got to do a few steps with them in order to use them in your application. And I've captured those as convert, transform, processing and optimization, generating a mesh, and geolocating them properly. So we'll go through those one by one, with the step one being convert. And this is simply converting it from whatever source format it was into a format that you like working with. I'll almost exclusively be using GeoJSON for this stuff because it's human readable, it's fairly succinct for what it does, and there's a lot of tooling support for it. The next step is to transform it. And so I'm using a tool here called OGR. Next step is to transform it. And this is the idea of converting it from that world coordinate space that it was captured in to the coordinate space that you want to use inside your application. So in this case, we have Archerfield Airport from a data source in the Queensland government in Australia. And you can see the numbers on the coordinates here. It's kind of the distance from the middle of Australia, Y and X. And what I actually want, though, is the latitude and longitude for this stuff, because that's what my app control that I'm building uses. So I just need to convert that. And the way to do these previous two steps is using a tool called GDAL. I found it to be the most friendly and accessible and powerful as well. And GDAL, it is a library that you can consume in Python or C++ or whatever, but it also has a bunch of command line tools. So in this case, I'm using OGR to OGR, which is just a transforming tool. I say I want it in the format of GeoJSON. I want the target spatial reference system to be EPSG 3857. So you can look up these on epsg.io. And I want to write the output to archerfield.geojson. And in this case, the input comes from archerfield.kmz, which is a KML file. So after I've done that and I've got my nice GeoJSON, I want to sort of process and optimize this thing. It's rare that the GeoJSON that you receive will be the format that you actually want to render raw. You'll want to do some things like filter out pointless parts. You might want to take a bunch of points and draw a hull around them. And you'll almost certainly want to optimize it as well. So I use a tool called turf.js, which is a powerful JavaScript tool for dealing with GeoJSON files. And it has a lot of support for the functions that you want to do. You can see we've got more code here to do, plumbing than I do doing actual work. So in this case, I'm reading in a GeoJSON file, which is about the federal airports around Australia. And my goal here is to get a simplified version of Archerfield Airport that I can render. So first thing I do, I read in the files. I then flatten that out because Archerfield Airport is actually made up of a whole bunch of different geometry, different polygons, not just one polygon. I sort of want to flatten that out so I don't have to deal with multi-polygons. I just want a whole bunch of polygons that are all called Archerfield. So I flatten that out. I then go through those filters, those features, and I filter them to just keep Archerfield. And then I rewind those. And what that means is often in these geographic systems, you don't really know if you're going to get it with the polygons defined in a clockwise order or an anti-clockwise order. And turf.rewind just make sure it's always in the same direction. Finally, we want to simplify that because there's too much detail in it. And I write it back out to a GeoJSON file after that. So the importance of the optimization step, I don't think can be understated. So here is one of the shapes from Archerfield Airport at its full detail and taking it down to 20% of the detail using that simplification algorithm. Still keeps the general shape, but you miss out on some details like the little spikes that come out and stuff like that. But the reasons for doing it are pretty clear. Once I use an ear clipping algorithm here to triangulate that mesh, you can see there's a pretty big difference in the number of triangles that are used between them. So we're going from 2,500 down to 500 triangles without losing a whole lot of detail. So this will be on a case-by-case basis, of course. How much detail do you want, and whether you want to do this automatically like I have, or whether you want an artist to trace them around. Yeah, it depends on your product. So this generates the basic mesh for a flat uh, structure coming from GeoJSON or from a feature in a geo database. A lot of the times we will want to extrude those so we can actually make use of the full 3D. So this is where those custom properties start to come in a bit handy. So in this case, we've got a building outline that has a height property with a height of 34. So when we get that, we do our ear-clipping algorithm. We can just extrude that polygon down. So walk around the outside, generate a few quads in that, and then put them in there. And this is the bit that really depends on the kind of artwork that you want here. So the UV coordinates that you choose as you're going around it, if you want to display things like windows or weatherboards or whatever, depending on the kind of building. If your properties have details about what kind of roof it has, is it pitched or is it arched, then you can even generate more realism here. But as a base level, you can do this will get you going into a base level for buildings, and then you can get your artwork to iterate and iterate on top of that. So when it comes to these features, thinking about the coordinates that you want to render them in is also important. So you built out this polygon, but what units are you using for this polygon? Are you converting it into meters, or are you going to keep it in latitude and longitude? And that's a decision you have to make depending on the way that you want to render it. But again, you can do these coordinate transforms. The way I like to do my buildings, or features that are building sized, whether it's plot plans or whatever, is that when I build out my mesh, I find the center point of all the points. I convert those latitude and longitudes to meters from that center point, and then I use that as the mesh that I have, so that on the ground in the center is my origin, my pivot point, and then from there I store metadata about what the latitude and longitude and altitude of that pivot point is, and then in whatever mapping library I'm using, I just put a map pin there and place it down, and there I go. The other thing you'll learn is that elevation ruins everything. So these systems that you're pulling the data from, they don't really account for hills that much. If you say that a building is 30 meters high, is that from the highest point in the hill or the lowest point in the hill? If it's on a hill, everything's on a hill. So you might have to do some little hacks there. Something that works well for buildings is to make that the center point, but then just extrude down as well, so it goes through the ground, and then it'll just be culled from occlusion, so you won't see it, but it'll never have that view of floating off the ground. But that's just a consideration you need to be pretty careful of. The final aspect of GIS that I want to touch on is LiDAR. So LiDAR is point clouds, and here is an example of a point cloud. We see here it's an area, a place called Noosa in Queensland, and that image at the top just colors it by altitude. So the higher points are red and the lower points are blue, but you can see the layout of the terrain from that. So while that one's colored by altitude, there are a whole bunch of other useful ways that you can slice and dice point clouds like this. So one of those is classification. So usually when you get point clouds, they come as classified point clouds, which means that each point on that cloud has a particular classification. It could be vegetation or buildings or terrain, as I've mentioned here. It could also be roads or water or a whole myriad of different ones. So this is great because it means that you can extract different parts, you can visualize them differently, and you can build something like this. So in this case, I've extracted those points for vegetation, triangulated those points. I've done the same for buildings, and I've done the same for the base terrain layer as well. And I've colored the vegetation green, I've made the buildings gray, and I've just put the terrain layer as the satellite imagery for that tile. And if we have a look here, we can see that it rendered okay. Like you can recognize what this place is. It's not fantastic because it was a really, really cheap and easy solution to do it. I'll go into a better way to do it in a sec, but just showing you some of the power of these point clouds to get visualizations quickly that give you that depth. There's certainly options around for that. So as far as tooling for LiDAR data, there are two that I reach for all the time. The first one is called LAS tools. So LAS is the file format that point clouds often come in. And this is, it's a free and commercial set of tooling depending on your usage and depending on what tools you're using. But its benefit is that it is super, super fast, and the basic functionality that it does is easy to use. So just viewing a point cloud, I haven't seen anything that can do it faster than the last tools here. But also merging point clouds together and simplifying them, reducing extra point, like removing noise and things like that. It's a very fast tool for those things that are common and don't need much custom effort. The other tool that I like though is PDAL, which stands for Point Data Abstraction Library. And again, this is similar to GDAL, but for point clouds, and allows a lot more power when it comes to processing point clouds. Again, it can be consumed either as a library for a custom application, or it has some powerful command line tooling available to it. So the most powerful command line tooling with PDAL is its pipeline tool. So this allows you to define a pipeline for a point cloud and do things with that so that you can then automate a lot of the processing of it. So in this case, I have a point cloud and I essentially want to extract buildings from it and get a pretty reasonable representation of those buildings. And this is how I've gone and done it. So my first pipeline is one that I just combine all of the LAS files that I have. So I input all of the data at the top there. I want to filter them so that I only keep classification 6, which in this case is buildings. I merge all of those point clouds together into one point cloud, and then I output it into a combined point cloud. I did this in its own step, basically for caching reasons. I didn't want to process the full point clouds every single time. I wanted to iterate on my algorithm for making buildings, so I made a small pipeline to begin with. But the next stage is where I get a bit more interesting, and that is actually building buildings out of the pipeline. And so in this case, we have a whole bunch of points. And the thing about buildings is they tend to have differences, like distances between them. So think of your house. You've got distance between your house and the house next to yours. And so I used a cluster filter here, which says that find me clusters of 100 points or more, where the points in that cluster are all within 1.5 meters of each other. And that was just numbers that I chose that worked well for my data set. Feel free to tweak them or whatever as you need to. The next thing is I group it by the cluster ID. So in this case, it creates kind of a separate point cloud for each cluster ID. And then I filter out the ones that that didn't actually get a cluster ID assigned at all. So basically, I keep the ones that have a cluster ID of 1 or higher. So they're the only ones I keep. If they didn't get a cluster ID, they must have had less than 100 points in the cluster, or just been single points that I don't care about. So this might not have caught all the buildings. They've got enough of them for our purposes. The next bit is reprojecting. So once again, this is down to the coordinate systems. EPSG 28356 is one that Australia uses. Again, GDA 94, but I actually want this in latitude and longitude, so I convert it to EPSG 4326 for my own processing reasons. And then I output this to a file, and in this case, I want it to output to GeoJSON. Sometimes you want to output to another point cloud. Sometimes you might want to output to GeoJSON, just so you can process it in something else. So note these things are still points. They are not they're not polygons or anything like that. So now that I've got my GeoJSON though, I can go back to turf.js and I can iterate on those as well. So here I load the GeoJSON as before. I go through the features. I extract the coordinates of each of those features, each of the points in the features. In this case, I know they're just points because that's what I output, and I create points out of them. I then tell turf.js to build a convex polygon around each of the points there, and essentially draws an outline around those points. And then I set the height property. Remember, features have properties, and so I set the height property as the average height, which I didn't put the code in here. I calculate the average height of each point and say that's the height. In this case, the LiDAR data that we were having were from drones flying overhead. So most of the points were the roof. We didn't have much detail about the walls, and so the average height was good. You could use maximum height here as well as an alternative. It's up to you. And then with that, I could bring that GeoJSON into my game engine. I could do my polygon creation, which I won't reproduce the code here. Just look up ear clipping algorithms and extrusion. And we have those buildings that were extracted from LiDAR rendering in the right place on a map tile here. So this particular data source is using Bing Maps for its base imagery and a Bing Maps control within Unity. The final bit that I want to touch on, and I will only be brief on this one, is 3D tiles. This stuff is amazing. It gives you much more detail than just sort of a height map that you'll get from normal tiles, normal elevation tiles, but the data sources for them are pretty rare. So you've probably seen Microsoft's Flight Simulator, and it's amazing, and they would mostly be built from these 3D tiles or from some procedural generation on the fly. But the easiest way to have a look at some 3D tiles and be amazed at their possibilities is actually the Maps for Windows application. So there's like 20 locations around the world that Microsoft have mapped out 3D tiles. And yeah, that's the format that Maps for Windows uses. Essentially, it's the same as a 2D tile in that it has a tile ID, but rather than being an image, it's a GLB file. So it has mesh and materials and yada yada yada. So have a look at that. It's a pretty cool standard, and a provider of that standard is Cesium. If you want to have a look at that, they've got some open source libraries if you want to use this sort of stuff. If you can source some 3D data. But I found the hardest thing with 3D tiles is just finding the data for it. There's not a lot of it around. So you could build it up from LiDAR data if you were clever enough, which I'm not. Okay, so that sort of is the end of what I wanted to talk about with GIS. It's a pretty dense subject, and I tried to cover a lot of the foundations there. I just want to reiterate that you don't want to be rolling this sort of stuff yourself. Have a look at other people's implementations. Don't think, oh, how can I convert between these coordinate systems? Don't think about how can I make the tiles pop in and out as I pan my map around or anything like that. There's controls for that sort of stuff, and they're marketed on location gaming or mini map style view where you have a top down view, and they're very powerful. I've mostly seen this from a Unity perspective, but I know they exist in other languages, other game engines as well, and certainly worth looking at. So yeah, that leads me to the end of my talk. I think I'll go over to the real live version of myself to take some questions now. So if my shirt changes color, don't be afraid. But thank you for coming. Thank you for watching. And I'll look forward to answering your questions soon.
Hi, Steve.
Hi, Alexander. How you doing?
Hi. For you, I think it's good morning or no? Yeah, it's good morning, I think. Yeah.
Yeah.
It's
8 o'clock in the morning.
Here. Yeah, it's around. it's 11:30 already here.
Right.
And we still have a long time to go. So, hey, great, Steve. Thank you for the presentation. I just checked if there were any questions. There aren't at the moment, but I actually had a question of my own. So this is actually really interesting to use GIS data to create three-dimensional environments. And the cool thing about it is that you actually build something up from dynamically based on that. So I actually have two questions. I'm just thinking about, can I do this really dynamically? So for example, if I want to do it augmented in a device, is that possible, or do I need to generate it up front?
Yeah, so that kind of depends on what data you're using. So my later example showing the LiDAR data and generating buildings from point clouds, you're not going to be able to do that sort of thing in real time yet. But if you're just dealing with basic base layers like the tree generation and the terrain generation in my first example, that stuff is completely real time, pulling from data sources that are online. And then you can even use it in augmented reality, as you said, by using the GPS and finding some way to align it with the world. Yeah, and you could mark out feature points and things like that just based on that. Yeah.
But it would require a big connection, I presume, because of all the data.
Well, no more than Google Maps already gives you is one of the cool things about this. So when you load up Google Maps, you're already pulling down satellite imagery and things like that. It's the same data. It's just, it might be a little bit more for the elevation, but yeah, it's the same kind of data. So it's the same bandwidth requirements, really.
And another question I had was, if something wants to start with this, so of course your presentation is very good and explained what to do, but what would actually the best way to start if I want to start with GIS data? So,
Yeah.
for example, I've never worked with it, but I really like this because you can do a lot of stuff. I'm myself am a mixed reality person, so I'm really interested in how you can actually use this in combination with 3D visualization. So what would be the best way to start with something like this?
Yep. So I think the easiest way is, if you're familiar with Unity, then go to Google or go to Bing or go to Mapbox, and they have pre-existing controls to do a lot of this for you. So the examples that you saw, that second example was using Microsoft's Bing control, which all you need to do is put in your Bing developer key, which you can get for free. And you've got a really, really rich 3D map that you can use, that you can plonk in your room, that you can move around like a mini map style thing. And that's a good way to just explore what's available, what's possible, the kind of level of detail you're going to get, and how you can start interacting with the world there. The downside with the Bing one is that it doesn't really support the immersive scale, like the putting it in your world, putting in VR style rather than just a mini map. I found that Mapbox is probably the best one. Again, they've got their own Unity package for that. And yeah, it just allows you to put in a GPS coordinate, tell it how you want to display things, and it will render them for you for the most part. And then you can go into Mapbox and add your own data sources if you have your custom stuff that you want to include
because
as well.
It becomes really interesting to combine it with other data sources, like, for example, cars driving around or vessels in the ocean, which where you can actually see where they are located on the world map.
Yeah, we've seen a lot of interest in enterprise, especially using data coming from IoT sensors and things like that to do exactly what you say. You know, what are the traffic lights saying at the moment? Where is the problem occurring in this gas pipeline? And you can bring that into your GIS world and, you know, see what's happening under the earth, not just on top of the earth, like you would in a top-down view, and get that idea of depth coming through and everything as well.
Yeah. Thanks. There are further no questions. So again, thank you for participating as speaker. Really glad to have you, and hope to talk to you soon.
Thanks, Alexander. I'll see you later.
Bye.